Hi, I'm Beth Faber at the Hydrologic Engineering Center, and this is lecture 2.3 of the Prospect course number 209, Risk-Based Analysis using the FDA software. This lecture will talk about incorporating uncertainty into the computation of expected annual damage. The topics we'll discuss are first, the traditional computation of expected annual damage without uncertainty. This is the computation we'll build on when we do incorporate the uncertainty. Then we'll talk about Monte Carlo simulation because that's the method that we'll use to incorporate uncertainty. Next, we'll talk specifically about the way the FDA software uses Monte Carlo simulation with a method called curve sampling. And finally, we'll talk about metrics other than EAD that these computations are going to allow us to consider. We're going to have a separate video for each of these topics, so only the first will be in this video. And there will be 3 more videos covering those other 3 topics. So now we're going to start with just the first. So in the previous lecture, the probability and statistics review, we saw that the expected value is just the mean of a probability distribution. So the expected annual damage is just the mean of the probability distribution of annual damage, otherwise known as the damage frequency curve. So to consider EAD, to understand it well, I find that it's interesting to interpret EAD as the average damage over a long period of time. So here we see that most years have no damage at all. Some years have some damage. Occasionally there will be a lot of damage. But if we average those damages with all those zeros, we'll get this blue line, which is the average over a long period of time. This is not necessarily a value of damage that we expect to happen. It might not be possible that we can get this amount of damage at all. This is like the 6-sided die that we saw in the last lecture. The roll of a 6-sided die has the expected value of 3.5. It's not a possible value. It's just the middle of the probability distribution. But it's a value that we can see as the average over many rolls. And here, expected annual damage is the average over many years of outcome. Right? So this gives us an annualized value. So back on this previous slide, annualized value can be compared to the equivalent annual cost in a cost-benefit analysis. Now, from a planning perspective, remember that to be used as benefits of the project, the expected annual damage is considered as the EAD reduced between the without project condition and the with project condition. So, although it's helpful, I think, to think about EAD as the average damage over a long period of time, we don't actually compute it that way, right? We develop a damage frequency curve. And we develop that curve by using relationships that summarize our other disciplines of hydrology, hydraulics, and economics. So we combine a flow frequency curve with a flow stage relationship and a stage damage relationship. And as you see, if we have flow in both of these curves and stage in both of these curves, it lets us relate frequency to damage. So these 3 curves can combine into a damage frequency curve. And then we just take the mean of the damage frequency curve to compute EAD. So I believe you've seen this computation in one of the lectures on day 1. I'm going to run through it again just because there's some ideas I'd like to introduce. So here's our 3 summary relationships, capturing our hydrology, can I say the word? Capturing our hydrology, our hydraulics, and our economics. Okay. The first is the flow frequency curve that we developed in the last lecture. And recall this was just the probability distribution of the annual peak stream flow in a cumulative form. So below we have the more common ways of representing probability distributions. We have the probability density function and the cumulative distribution function, or CDF. And this flow frequency curve in the frequency curve form is just the CDF, but with 2 axes switched such that we have probability on the horizontal axis. So I want to introduce an idea that I didn't mention in the last lecture. We talked about how the area underneath the PDF is probability. What I didn't mention was that the area between the CDF and the probability axis is a way to compute the mean. So in the frequency curve form up here, this would be the area underneath the curve because probability is on the horizontal axis. So this is not something we need for an analytical probability distribution where we can compute the mean from the distribution equation and the parameters. But for a graphical probability distribution that doesn't have equation or parameters, this is a necessary way of computing the mean. And the damage frequency curve is generally a graphical frequency curve. So we'll be using the area underneath the frequency curve to compute the mean. So for our other summary relationships, next is hydraulics. So this is the flow versus stage relationship, and it summarizes the results of all our hydraulic modeling of the location, including the channel and the overbanks, and sometimes the interior, although sometimes the interior is captured in a different relationship. Then for the economics, we have the stage versus damage relationship. This summarizes the structural inventory, including the values, the damage assessments, and also the topography. Now, if we take these relationships and line them up so that their axes match, so we have flow and flow, we have stage and stage, we have damage and damage. So this will allow us to build the damage frequency curve in the lower right. Right, so for any given value of exceedance probability, the frequency curve suggests a flow. We come over to the second curve and get a stage, come down here and get a damage, and so that damage pairs with that exceedance probability. Do that same thing right across the exceedance probability axis, and we can trace out the damage frequency curve. Our last step was to take the area underneath the damage frequency curve as our computation of the mean, or the expected annual damage, or EAD. So it used to be that that was our risk analysis, right? We have probability, we have the flow frequency curve that represents the natural variability in stream flow that translates down to the probability of damage, and then we have consequence, which is damage itself. So having combined probability and consequence, EAD is a measure of risk, right? And that used to be our complete computation. But each of these summary relationships that captures so much information and analysis, each of these relationships includes uncertainty. We don't know quite precisely exactly how these curves are drawn and where they lie. Right? So I'm representing uncertainty on this slide in two ways, with PDFs and with confidence intervals. Right? So these PDFs, you should visualize these coming out of the screen on a z-axis. This PDF, or probability density function, represents the uncertainty in where this curve actually lies. So for a given exceedance probability, this represents the range and likelihood of what the value of flow that has this exceedance probability might be, right? So where the curve is the highest, I have the most likelihood of it being. So it's most likely to be fairly close to my best estimate, but it can be lower or higher with decreasing probability. These PDFs representing this uncertainty exist all along the length of this curve. Now, if I take this PDF and span 90% of the middle of it and knock 5% off of either tail, then I can draw a 90% confidence interval. And I can trace that 90% confidence interval from the PDFs all along the length of the curve. Right? So the 90% confidence interval is a bit of a simpler way of depicting the uncertainty, so our pictures are a little bit clearer, right? But I include the PDFs here as a reminder that the uncertainty across this 90% confidence interval isn't uniform or flat. We have more likelihood of being near the best estimate and decreasing likelihood of being further away from the best estimate, and we have a 10% chance of being outside the 90% confidence interval, 5% chance of being above and 5% chance of being below. So these are knowledge uncertainties, right? And these exist for all three of our summary relationships, right? For any given flow, we're not quite sure what the stage might be, and we can evaluate it with our hydraulic modeling, but we don't get a precise value. Down here, for any given stage, we don't know quite what the damage is going to be. Right? So we have knowledge uncertainties across all three of these relationships, and that leads to knowledge uncertainty in the result. Right? So we need to be able to evaluate the uncertainty around the damage frequency curve and the EAD. Right? So how do we include the uncertainty? Well, the first step is going to be to estimate the uncertainty about each of these relationships. Right? At this point, I've kind of skipped over estimating the uncertainty and jumped right to how we're going to incorporate it, but it's very important to consider how we estimate the uncertainty. That's going to be done on day 3 and day 4 in 3 separate lectures. One lecture for each of the summary relationships that talks about how we define the uncertainty around each of them. right? Once we have that uncertainty defined, we're going to compute the expected annual damage many times with different possible versions or realizations of each of the curves from within its uncertainty. Right? This method is called Monte Carlo simulation, and that's what we're going to talk about next. So if you have any questions about either the EAD computation or the depiction of uncertainty that I described, please go to the discourse site and type your questions there, and I'll try to be monitoring it real time to answer your questions. And next we'll talk about Monte Carlo simulation in the next video. So that's the end of this one. Thank you.